In this video, I will share with you how to find vertical and horizontal asymptotes of rational functions. Now we have looked at asymptotes in that basic 1 over x and 1 over x squared graph, so we'll now kind of generalize the process of finding asymptotes. Just to recall, an asymptote, which is A-S-Y-M-P-T-O-T-E, is a line that the graph of a function comes very close to but does not touch. There is an exception to this for some of the horizontal asymptotes that we'll talk about, but really this means as we go to the extreme ends of the graph, the function is approaching that asymptote. There are three types of asymptotes. There are vertical asymptotes, and remember vertical are ones that run up and down. There are horizontal asymptotes. So these are going to be lines that run left and right. Think about the horizon. And then there is something called slant or oblique asymptotes. We talked about this terminology when we dealt with lines. So a slant line is one obviously that's not horizontal or vertical. It has an angle to it. We are not going to focus on those in this course, but I thought it was important for you to know that those do exist. So a vertical asymptote is a vertical line, so it does have an equation of the form x equals h. This line is a vertical asymptote of the function f of x if, as x approaches h from the right or left, y is approaching positive or negative infinity. And recall we saw this behavior around x equals 0 for the graph of 1 over x and 1 over x squared. Do you remember as we came in from 0 from the left and right, the graph went almost vertically straight up, but it was getting closer and closer to that y-axis or that graph of x equals 0. So we're saying that the function goes to positive infinity or negative infinity as x approaches h from the right or left as shown. So you can see from my graph here. So when we look at the ends of the graph near that asymptote, we see that it's going either upward onto infinity or downward to negative infinity. The graph of a rational function will never cross or touch a vertical asymptote. And if you recall from the function 1 over x and 1 over x squared, x equals 0 is where the function was undefined, and so that is that there's not going to be a function value that corresponds to that particular x value, which is why it can never cross or touch that vertical line. So finding vertical asymptotes, if they exist, they are located at the values a rational expression is undefined. If our rational function r of x is equal to p of x divided by q of x, where p of x and q of x are polynomial functions with no common factor, and q of x can't be 0, then x equals h is the equation of a vertical asymptote of r of x if q of h is equal to 0. In other words, the value of h is a 0 of the denominator of the rational function. Now, while we've seen a rational function like 1 over x or 1 over x squared only have the one vertical asymptote, a rational function can actually have 0, 1, 2, or more vertical asymptotes. It just depends on how many values make that denominator 0. There's a special case. If the polynomials in the numerator and denominator have a common factor, then the rational function can have a whole at one of the zeros rather than a vertical asymptote, and one of our examples will illustrate that. So in this example, we want to determine the vertical asymptote, if it exists, of each rational function, and then state the function's behavior around that vertical asymptote. Our first function is f of x equals 1 divided by x minus 3. So to find the vertical asymptote, and remember we're looking for an equation, we want to set that denominator equal to 0. So we set x minus 3 equal to 0 and solve to get x equals 3. So the equation of our vertical asymptote is x equals 3. Now, to determine for sure that it is a vertical asymptote, we can notice that as x goes to 3 from the left and x goes to 3 from the right, that the function values or y values are going to either positive or negative infinity. And so if you take a moment and replace x with these values, let's say 2.9, so again we're looking at, we have a coordinate system, and here is our x equals 3. We're saying that's a vertical asymptote. We want to see what happens to the right of 3, which is as x approaches 3 with a plus, and as x approaches to the left of 3, which is as x approaches 3 with a little minus sign. If we replace x with 2.9, we get 1 divided by 2.9 minus 3, which is 1 divided by negative 0.1, or negative 10. Replacing x with 2.99, we get 1 divided by negative 0.01, which is negative 100. If we replace x with 2.999, we get y is 1 divided by negative 0.001, or negative 1,000. And the last value of 2.9999, when we replace x into the function, we get a negative 10,000. Likewise, on the right side of 3, 3.1 replaced in for x, we get a 1 divided by 0.1, or just 10. 1 divided by 3.01 minus 3 is 1 divided by 0.01, or 100. And then we'll get 1,000 when x is 3.001, and 10,000 when x is 3.0001. So we can see that as x is approaching 3 from the left, the y values continue to get larger in the negative direction, so those are approaching negative infinity. As x is approaching 3 from the right, the y values are getting larger in the positive direction, so those numbers are approaching positive infinity. So what we would expect to see is from the left side of the graph is going down as we get to that asymptote, and on the right side it's actually coming closer and closer and going upward. Now we have the function f of x equals negative 3 divided by the quantity x plus 5 squared plus 1. So the vertical asymptote is found by setting that denominator, x plus 5 squared, equal to 0 and solving. Well, the only quantity that gives us something squared equals 0 is 0. So we know that x plus 5 has to equal 0, or that x is negative 5. So now we can approach negative 5 from the left and right. And if we replace x with negative 5.5, negative 5.4, negative 5.3, negative 5.2, and negative 5.1, I'll just tell you what these values are. You can actually substitute them again on the calculator and figure that out, but you should get negative 11, negative 17.75, negative 32.33, negative 74, and negative 299. If we replace x with values that are on the right side of negative 5, like negative 4.5, negative 4.6, negative 4.7, negative 4.8, negative 4.9, we get very similar values. In fact, we get the exact same values: negative 11, negative 17.75, negative 32.33, negative 74, and negative 299. And so as x is approaching negative 5 from the left, notice that our y values are more and more negative, right? They're going down to negative infinity, and they're doing the same behavior as we approach negative 5 from the right. So we would expect to see a graph that is approaching the asymptote in a downward direction. Part C is f of x equals x minus 1 divided by x squared plus 2x minus 8. To find the vertical asymptotes, we have to set x squared plus 2x minus 8 equal to 0. Notice that this is a quadratic equation. To solve this, we're going to try factoring, and it does factor. If we look at the factors of 8, whose difference is 2, that would be a 4 and a 2. And the larger sign needs to be positive, and the smaller will be negative. So our asymptotes occur at x plus 4 equals 0, or x equals negative 4, or at x minus 2 equals 0, which is at x equals 2. Now, I've actually drawn a picture of the graph here for you to see that we do have two vertical asymptotes for this graph, and you could enter this on your graphing calculator. You would just need to be very careful to put parentheses around the numerator and denominators expression so that it graphs correctly. Now, looking at the graph, I won't go through the process of plugging in the numbers, but we can confirm the behavior, right? As x approaches negative 4 from the right, and as x approaches negative 4 from the left. We also need to determine what happens as x approaches 2 from the right and as x approaches 2 from the left. What does y approach? As x approaches negative 4, so this is our asymptote to the left of the origin, 4 units left, we're looking at as x approaches negative 4 from the right, so that's on the right side of negative 4. What is our function doing? And notice that our function is going in the upward direction there as it gets very, very close to that vertical line, and so we say there that y is approaching positive infinity. As x is approaching negative 4 from the left, so coming in on the left side of that vertical line, notice that our function is going downward as it's approaching that vertical line, and so we say it's approaching negative infinity. As x approaches 2 from the right, so on the right side of 2, the function is going up very, very close to that vertical line x equals 2. So we say y is approaching infinity. And as x approaches 2 from the left, on the left side of that vertical line, we see that the graph is going down. And so we say y is approaching negative infinity. Part D is f of x equals x minus 2 divided by x squared minus 4. We can start by looking at what the vertical asymptotes would be if we set x squared minus 4 equal to 0. We would have the difference of squares, so x minus 2 times x plus 2 equals 0. Therefore, we get that x minus 2 equals 0 at x equals 2, or x plus 2 equals 0 at x equals negative 2. And so if we don't examine the graph or examine the function any further, we would say that there's a vertical asymptote at both 2 and negative 2. But this one is actually a special case, because notice that one of our factors of the denominator is actually also in the numerator. So this function, x minus 2 divided by x minus 2 times x plus 2, actually simplifies to 1 divided by x plus 2 when we divide out that common factor. Now, we can't change the fact that the function is undefined at both 2 and negative 2, but what that tells us is that there is indeed a vertical asymptote at x equals negative 2, because that's still in the simplified version of the function, right? X plus 2 is still in the denominator. But there's going to be a hole in the graph at x equals positive 2. That 0, what we say, was divided out. It has what we call a removable point of discontinuity. And so that was divided out, so that leaves us a hole in that particular graph there. And we can observe that if we graph the function. The other way you would know that, if you actually plugged in this graph into the calculator, and when you plug it in, you have to use the original function, not the simplified version. If you plug that into your calculator and graph, you'll know that that as we approach 2 from the right and left, the graph is not going to positive or negative infinity, so that tells you there's not a vertical asymptote there. It would just be a hole. You will see the fact that it's undefined at x equals 2, which tells you something's going on, but the behavior around that value of 2 is not what it is for a vertical asymptote. So let's just write that behavior down as x approaches negative 2 from the right. What does y approach? So as x approaches negative 2 from the right side, the graph is going up to positive infinity. As x approaches negative 2 from the left side, y is approaching, right, it's going down, which is negative infinity. And so as x approaches 2 from the right and left, this point is actually approaching whatever it is whenever we plug in 2 here, 1 divided by 2 plus 2, which is 1/4. So as x approaches 2 from the right, y is approaching 1/4. And as x approaches 2 for the left, y is approaching 1/4. So in that instance, when we can actually substitute the 2 into that simplified function, that will be the value that the function approaches there.